Since we've spent quite a bit of time going over the mathematics of curved mirrors and the sign conventions and the equations and such, and we spent a little bit of time going over the sign conventions and the equations for curved lenses, we'll go straight into checking our homework this morning. Okay, that'll serve as our review for this stuff this morning, is going over a couple of these questions. We had two sets of homework from Monday, and they were due for today. First of all, we had page 681, question 1 of 3, and then we had page 683, some check and reflect questions. Any issues first on page 681? Number 3? Okay, 681, number 3. Any others? Nope. All right, 681, number 3 says, a projector uses a converging lens. As soon as we see that word converging lens, we're going to say that it's a positive focal length. Now, this is the one that if you forget to write down positive focal length, by default, you're going to be correct, right? Because you're going to forget to put a negative or a positive in there, and it's going to just be a positive, so you're going to end up getting it right. I just want to write that in every single time because I want to be in the habit of identifying whether it's a converging or diverging lens or mirror. Okay, I want to be in the habit of writing down positive or negative so that when it becomes a negative, I don't forget to do it. It's a converging lens to create a focused image on a screen that's located 5 meters away. That's going to be my DO, 5 meters away. Look, the image is formed at that point away from the lens 5 meters away. It's formed on a screen, so that means we know it's what kind of image, real or virtual. It's got to be a real image. You can't project a virtual image onto a screen. It's a real image on a screen, and therefore it's got to be a positive 5.0 for the object distance. Now, the image is generated from a slide that's located 7.5 centimeters from the lens. The slide is going to be my object, and if that's 7.5 centimeters from the lens, we're going to call that DI. Although we do want to be careful here with units. Usually it's centimeters we're going to circle. In this case, we're going to circle the meters, because usually in these questions we're dealing with centimeters, right? Bottom line is it doesn't matter, but we have to circle one or the other because we got to be consistent. We've either got to convert both of them to meters or both of them to centimeters. Okay, my suggestion in these problems is go centimeters. It's probably a little bit easier. What's the focal length of the lens? We're looking for F, and we're looking for the magnification, M. It probably stands to reason that for this one, we're first going to say the thin lens equation, 1 over F is equal to 1 over DO plus 1 over DI. 1 over F is equal to 1 over DO. What are we going to make DO? We're going to make it 500. If we're going centimeters, that is, we're going to make DO 500. If we're going meters, then we're going to leave it. We're going to change DI to 0.075. Centimeters, though, DI is just 7.5. Okay, let's pull out the calculator and let's make sure we can do this. Okay, we've shown you this a million times on the calculator now, so I think we should be good with this, but just in case, we're going to say 500 to the minus 1 plus 7.5 to the minus 1. Let's flip that over. We get 7.39. 7.39 centimeters. Is that good? Now we want to find the magnification. We've got really 2 equations that will give us the magnification, although they appear on your data sheet as one. It's HI over HO, and it's negative DI over DO. Since we don't know anything about the heights, we're going to use the second part of that equation, negative DI over DO. Negative 7.50 centimeters over DI, over DO, which is going to be 500 centimeters. Is that right? Yes, you're right. Yes, you're absolutely right. Now I got lucky with this one then, right? Okay. DI is 500. DO is 7.5. You're absolutely right. I got lucky with this one because in the end, if I said 1 over DO plus 1 over DI, it's the same thing as saying 1 over DI plus 1 over DO. But I don't get so lucky with the magnification here, right? The magnification is DI over DO, so it's going to be 500, negative 500 divided by 7.5. Thank you. You know what the lousy thing about this is? This is a multiple choice question. And I did my division of 7.5 over 500. That answer probably would have been there. Okay, and I probably would have saw that, and I probably would have picked it and said, oh, I'm probably right because I got an answer that's there. So be careful in that. Try not to make those silly mistakes that I made, okay? If you have time, check over your work. Do that division, we get negative 66.7. Now they have it written as 66.7x. Okay, doesn't matter. Okay, there's no units with it. The x just means times. The object is, or the image is 66.7 times the size of the object. What do we know about this image? Real or virtual? Real, it's projected onto a screen. We don't know anything about upright or inverted in terms of whether it's been flipped over from the object or not, but we do know that the image is going to be, we don't know whether it's upright or inverted in terms of which side of the principal axis it's on, because we don't know which side the object is on. But assuming the object is upright, okay, we don't know that for sure, but assuming the object is upright, then the image must be right side up or upside down? Upside down. You know that because the magnification is negative 66.7, right? Makes sense? So it's got to be flipped over. Whatever side the object was on, the image is on the opposite side. All right, the second bit of homework that was due for today was page 683, number 1 to 2, 4 to 5, and 7 to 14. Any answers to those questions, please, on 683? Number 4, I heard. I got 4, 8, 10. 4, 8, 10, 4, 5, 8, 10, 13? Abby? No? I shouldn't have assigned number 4. Actually, I didn't mean to assign that one. Don't worry about that. No, don't worry about that. Sorry about that. That's irrelevant for us. Completely irrelevant for us. Number 5, we'll go over those. Suggest an experimental design to determine the critical angle for a lucite air boundary. Lucite or anything else air boundary. Anybody have an idea for that? How could you find the critical angle for anything with air? Glass with air, lucite with air, plastic with air, water with air? Yep. Well, yeah, that's the equation that will get it for us, but we want an experimental design as opposed to just a mathematical analysis to find the critical angle. What if we took a laser beam and we shone that laser beam, here, let's draw a little picture here. Here's my normal line. Okay, this is lucite. This is the one with the high index of refraction. This is air. This is the one with the low index of refraction. So we've got to be going from high to low index of refraction. What if we shine that laser beam like this? See what happens to it. What do you think is going to happen to it when we shine that laser beam like that? Do you think it's going to reflect or refract? We're at a pretty low incident angle there, right? So it's probably going to refract. It's going to refract away from the normal line because when the light goes from a high index to a low index of refraction, the light's going to speed up. So it's probably going to refract, but with an angle that's bigger than the incident angle. All right, well, that doesn't tell us much. Let's increase that angle of incidence a little bit. There we go. That doesn't tell us much. Let's increase it more. That doesn't tell us much. That doesn't tell us much. What does that tell us? That's the beginning of total internal reflection, right? That's the point at which reflection begins to occur. What do we call this angle up here that we did call theta 1? Critical angle. Now we can measure it with a protractor. So essentially all you have to do is shine a beam of light, probably laser light, at small increments, small increasing increments of angles away from the normal line until it begins to reflect. At the point at which it begins to reflect, you've just measured the critical angle. Now, the reality is you're probably not going to see this one. The first one that you're probably going to see that indicates total internal reflection has taken place is going to be this one. But the reality is it's only slightly more than this one. So that's good enough to tell you what the critical angle is. Okay. Number 8. Explain the effect of a wavelength on the index of refraction for a particular medium, light, glass. How does this lead to dispersion? That's a good question. Dispersion, remember, is the splitting up of light when it goes through a prism or something like that. What effect does wavelength have on the index of refraction? Here's my prism. Remember when we shone light, white light, on that prism, what happened to it? It split up, right? What color bent the most? And what color bent the least? What color appeared up here at the top? Red. And what color appeared down here at the bottom? All right. Which one has the higher wavelength, red or violet? Let's think of frequency. Which one has the higher frequency? No, they're all visible light, but visible light has a frequency range of 4 to 7.5 times 10 to the 14. So they all have a different frequency. Now, I think you're getting confused with, the frequency stays the same, right? Once a wave has been produced, the frequency stays the same, yes. But this isn't one wave. This is 7 different waves, right? Red, orange, yellow, green, blue, indigo, and violet. So they've all been produced, and they all keep their same frequency. It's just that they all have a different frequency than each other, okay? Which one has the highest frequency, red or violet? It's going to be violet, yeah. Okay, if red or violet has the highest frequency, then red has the highest wavelength. Because remember that high frequency corresponds to low wavelength and low frequency corresponds to high wavelength. Red low frequency, high wavelength, violet high frequency, low wavelength. All right, what effect does wavelength have on the index of refraction then? We know that red must have the lowest index of refraction, or I should say that this glass must have the lowest index of refraction for red. That means that the smaller the wavelength, the greater the index of refraction, because smaller wavelengths refract more than do bigger wavelengths. Make sense? Red wavelengths, which are big, refract less, therefore a smaller index of refraction. I'm sorry? Yeah. The higher the wavelength, the smaller the index of refraction. Because you can see here that the high wavelength here, red light, refracts less than the small wavelength, which is violet light. Does this lead to dispersion? Well, if there's a different index of refraction for the glass for each different color, then of course the light's going to bend with each different index of refraction a different amount. In other words, each color is going to bend a different amount. If it bends a different amount, then it can't go through in the same place. It's got to lead to it splitting up, which is dispersion. 10. So it says a light ray is incident on a block of quartz glass and is equal to 1.47 at an angle of 35 degrees. What's the angle of refraction? We have to assume something here that isn't really stated, that probably should be stated. What is that? It's going from air. So we're going to say N1 is equal to 1.00. That's the index of refraction of air. That's on your data sheet. N2 is 1.47. Okay, the angle of incidence is 35.0 degrees. And we want to find theta 2. That's the angle of refraction. So let's say sine theta 1 over sine theta 2 equals N2 over N1. Don't we just make theta 2 equal to 90 degrees? Don't we always do that now? No, we only do that when? Yeah, we only do that when we're solving for the critical angle, and that's not what we're doing here. We're solving for the angle of refraction, which presumably is going to be less than 90 degrees, right? Because it doesn't say anything about reflection taking place. We're going to say sine 35 degrees is equal to, over sine theta 2 is equal to N2, 1.47 over 1.00. Let's take the sine theta 2 up by multiplying. Becomes sine 35 degrees is equal to 1.47 times sine theta 2. And it's technically over 1, but it just disappears somewhere, right? Take the 1.47 over by dividing. How do we get theta 2 there at this point? Yeah, Let's go sine 35 over 1.47 equals, get a number for that, and then let's take the inverse sine of that. When we do that, I'm not sure what we get, but I think we can all solve that now. Before you solve for that, Maureen, before you get that, let's assign the rest of those questions on 683, number 16 to 21 for homework for tomorrow. 16 to 21 for homework for tomorrow. And we're going to have ourselves that quiz tomorrow on lenses. Okay, just a mathematical problem using the lens equation and the magnification equation. Next topic. Here's one that we talked about at the very beginning of the unit, just very briefly. Diffraction. This was a property of waves. We said at the beginning of the unit that light undergoes diffraction, so therefore there's evidence to support the wave nature of light. What is diffraction? Remember from physics 20, diffraction is the spreading out of a wave. When a wave goes through an opening, it spreads out. And I found this picture on Google Images, thought it was the perfect picture to show diffraction, real diffraction, not just a hand-drawn thing that I can do on a board, but real diffraction of water waves. Here we've got our water waves going this way from out in the harbor or out in the ocean, and then it goes through this little opening here. You can see what happens to those water waves. The water waves spread out. They diffract. Refraction is the bending of a wave. Diffraction is the spreading out of a wave around a barrier or through an opening. We said that that's a property of waves, but that light undergoes diffraction, so therefore there's evidence to support the wave nature of light. Now, interference can occur when two waves, including two light waves, encounter each other. What does that have to do with diffraction? Well, if we have diffraction from two openings, like this, then we're going to have interference from both of those diffraction patterns. You can see on the left-hand opening here, we have a diffraction pattern that is more or less circular. And from the right-hand opening, we have a diffraction pattern that, again, is more or less circular. What I want to do right now is trace over some of these lines. I'm going to trace over my crests in green. So my crests will be green. My troughs of the waves will be blue. Let's make this a crest. Well, if that's a crest, then the next crest will be right here. The next one will be right here. Right here. We go to the next one, the other opening. The waves produced by the second opening are going to produce crests and troughs as well. Here's my first crest. Okay, my second crest. And so on. Every second one is a crest. To save ourselves the bother of tracing through those again, we're going to say our troughs are black. So what's left there are my troughs. Green is crest, black is trough. Now we've got a whole bunch of crests and troughs going everywhere, producing this mishmash of waves, right? What's the interference pattern going to look like? What's it going to look like when a crest hits a crest and a trough hits a trough? Well, you guys know from physics 20, when a crest hits a crest, we get a certain kind of interference. It's called constructive interference. Constructive interference means we get a bigger crest. Or if a trough meets a trough, we also get constructive interference. That means we get a bigger trough. So bottom line is when we get constructive interference, we get a bigger wave. If it's a result of two crests, it's a bigger crest. If it's a result of two troughs, then it's a bigger trough. What I want to do right now is identify in red the areas where we get constructive interference taking place. Where do we get constructive interference taking place? Well, we get constructive interference taking place where a crest meets a crest or a trough meets a trough. So everywhere where we see a line, two green lines coming together, we're going to put a little red dot. Everywhere we see two black lines coming together, we're going to put a little red dot, because that's going to represent areas where we get constructive interference. There's constructive, there's constructive, there's constructive. Okay, here's constructive. Again, everywhere where we get two black lines, two troughs, or two crests coming together, that's where we're putting the little red dot. I wouldn't panic about drawing this, guys. Okay, it's not the end of the world. I just want you to be able to see this, okay? Now let's put a little blue dot everywhere we have destructive interference. In other words, where a crest meets a trough. Where a crest meets a trough, that means we cancel them out, right? You get nothing. So let's draw those areas of destructive interference in blue, where green meets black. You should start seeing some patterns here. If we start joining these lines together, then we get these lines of destructive interference, and we also get these lines of constructive interference. The areas of destructive interference, that's where a crest met a trough, we call nodal lines. The areas of constructive interference, where a crest meets a crest or a trough meets a trough, and we get either a bigger crest or a bigger trough, we call constructive interference. And we call them antinodal lines. Now, if these are water waves, like it was in the picture that I showed you just a second ago, then when we're looking at them from above, we will see clear, distinct lines of constructive and destructive interference. We will see on the blue lines calm, smooth water. We will see on the red lines alternating areas of really big crests and really big troughs. Okay, if you happen to be laying on an air mattress trying to read a book on a blue line, you're going to be very comfortable reading that book, because you're just going to be sitting there on this calm, smooth water on this blue line, area of destructive interference. But if you're trying to read a book on an air mattress on one of these red lines, these antinodal lines, or these lines of constructive interference, then you're going to be bobbing up and down like crazy, because we've got really big crests and really big troughs. So you're going to be going up and down like this, as opposed to just lying there nicely on the blue line. If that's a water wave, that's what it's going to be. Now, if these are light waves, we're not going to see this. We're not going to see the areas of constructive and destructive interference here. The light has to bounce off of something in order to see it. So we're not going to see big, bright lines right here and dark things right here. The way we detect constructive and destructive interference lines, or antinodal and nodal lines with light, is to put a screen over here. Let's put a screen over there, like a piece of paper or a piece of cardboard or a wall or something that will reflect the light. If we do that, then we're going to see on that screen alternating areas of bright spots and dark spots. We're going to see a bright spot right here. That was where we had constructive interference. We're going to see a bright spot right here. Again, constructive interference. A bright spot right here, where constructive interference took place. A bright spot. A bright spot. In between, what are we going to see? No light. We'll call it a dark spot because there's no light there. There was destructive interference. So the interference pattern that's produced on this screen as a result of this diffraction and then interference of both the diffraction types looks like a series of bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. That makes sense. Now, if we take a look at that series of bright spots and dark spots again on that screen, like we showed you on the last page, it looks something like this. Right? Bright spot, dark spot where there was no light. Bright spot, constructive interference, dark spot where there was no light, destructive interference. If we plot a graph of the intensity of that light versus the position, so in other words, the position X along the x-axis here, the intensity, how bright the light is, then it would look something like this. Now, this is the best I could do with Microsoft Word, but really we should have kind of curves on the top there. It should be a little bit smoother. You can see that the middle line, the middle bright spot, is the brightest bright spot. And then as we go out from there, it becomes a little bit less bright. Okay, the intensity is a little bit less. Okay, the intensity is a little bit less. What do we see in between here? There's no bright spot, right? It's a dark spot. There's no light there. So what's the intensity right here? Or right here? Or right here? The intensity is 0. So this is what you physically see. This is a graph of what you see. Intensity of what you actually see. Intensity of the bright spots and the dark spots versus the position of those bright spots and dark spots. So this bright spot would have an intensity that was really, really high. This bright spot would have an intensity that's a little bit lower. This bright spot would have an intensity that's a little bit lower. That middle bright spot, that brightest bright spot, that central bright spot, we're going to call our central maximum. Our central maximum, because it's a maximum area of light. It's a bright spot. I'm going to label it with the number 0. The next bright spot to the right and to the left of it we'll call the first order maximum. We're going to label that with the number 1. Whoops. Say number 1 and then I write number 2. We're going to label them both with the number 1. The second order maximum, we're going to label with the number 2. The third order maximum, the fourth order maximum, the fifth order maximum, and so on and so on and so on. I just haven't drawn any more than second order maximum. The first order minimum, that's a dark spot, destructive interference, a nodal line. First order minimum on the other side. Second order minimum on the other side. We're going to make this 0.5. We're going to make this 1.5. Now, what I'm doing here is a little bit different than what you're going to see in a lot of books. Not all of them. Some of them use the system that I'm using here, but a lot of books use a slightly different system. But I think this way is better. I think this way makes it a lot easier for us to solve the problems that we have to solve. So if you ever see something a little bit different, if you ever see it labeled a little bit differently, that's okay. Doesn't mean they're wrong, doesn't mean I'm wrong. Okay, as long as you can both arrive at the same answer, then they're both right. So my first order maximum will be, we're going to say 1. My second order maximum is going to be 2. My first order minimum is going to be 0.5. My second order minimum is going to be 1.5. In other words, my minimums are going to be whatever the number is minus 0.5. My third order minimum would be 2.5. My 16th order minimum would be 15.5. My 17th order maximum would be 17. Does that make sense? So my maximum is the number. My minimum is, we're going to subtract 0.5 from it. I do that now. What a lot of sources, a lot of books do is do that in the equation. They have a couple of different equations for minimum and maximum. We use one equation that works for both minimums and maximums, and we just have slightly different numbers to accommodate for that. Now, there are a couple of equations that we're going to use to describe this. Two equations you see up on the board here right now. I'm going to redraw this so that we can label some of these variables, because most of these variables are going to seem kind of foreign to you right now. Here's my two openings. Okay, those two openings both diffract the light. Those diffraction patterns take place, those circles take place, right? produce an interference pattern that on the screen up here produces a bright spot, and a dark spot, and a bright spot, and a dark spot, and so on. This is my central maximum that we called 0. This is my first maximum that we called 1, and 2, and 3, and 4, and 1, and 2, and 3, and 4. And of course, the minimums, 0.5, 1.5, 2.5, 3.5, and so on, and so on, and so on. Let's try to figure out what these variables mean here now. Lambda, that's the easy one, right? That's wavelength. That's the wavelength of the light, and it's going to be measured in meters. It's going through these two openings, diffracting and interfering. The wavelength in meters. And that's going to be the same thing in both of these equations. D is going to be the distance between the openings. Distance between the slits. From the center of one slit to the center of the other slit. And that's going to be measured in meters. Now this is going to be a really, really small number. So this D is going to be, it's not like it's going to be 1 meter or 1.5 meters. It's going to be centimeters. It's going to be even smaller than that, millimeters even. Smaller than that even. It's going to be a really, really small number. So don't be surprised if you see D as 10 to the minus whatever. D is the distance between the two openings. So we're good with D now. L, right here, is the distance from the screen to the openings. However far away the screen is from those two openings that caused the diffraction and interference. I labeled it as a capital L there. In the equation, it's actually a lowercase l. I just can't do a handwritten lowercase l to not look like a 1. X, here's where it starts becoming a little bit trickier. X is also a distance. It's a little bit confusing here because D is a distance, L is a distance, and X is a distance. X is the confusing distance though. X could be the distance between the 4th order maximum and the 1st order maximum, or it could be the distance between the 3rd order maximum and the 1st order minimum, or it could be the distance between the central maximum and the 2nd order minimum. X can be any distance you want, from any maximum to any other maximum or any other minimum, or any minimum to any other max or min. It can be anything you want. Well, how does that work? We'll talk about that in a second. We'll reconcile that in just a second, okay? X is the distance from any maximum or minimum to any other maximum or minimum. Sorry? They'll probably give you X, yeah. So you're probably going to use the one that you were given. Okay? It doesn't really matter which one it is. From 1 to 4, from 0.5 to 3, from 0 to 2.5, doesn't really matter which one it is that you're given. But you got to understand that we're going to get a different number for lambda, right, if we have a different number for X. So how does that work? Well, the key is we can use whatever X we want as long as N is consistent with it. N is the difference between the maxima or minimum number. So for this one, we would say that N is equal to 3, because 4 minus 1 is equal to 3. For this one, we would say that N is equal to 2.5, because 3 minus 0.5 is 2.5. For this one, we'd say that N is equal to what? What's N equal to over here? 0 to the 3rd order minimum, N would be equal to 2.5. 2.5 minus 0 is 2.5. So X can be whatever you want, but N has to be consistent with X. Does that make sense? That's why we labeled all these 1, 2, 3, 4, 5 or 0.5, 1.5, 2.5, 3.5. So we could start subtracting the maximums and minimums here. 4 minus 1, 3 minus 0.5, 2.5 minus 0, so on. Not much left here. Theta is an angle, but it's always got to be measured from the central maximum. It can be the angle from the central maximum to the first order maximum. It can be from the central maximum to the third order minimum. Just 2 seconds here, guys, and then we'll finish up. To the third order minimum. It can be whatever angle you want, as long as it's measured from the central max. X can be measured from anything to anything. It doesn't have to be from the central maximum, anything to anything. Theta can be anything almost, but it's got to be measured from the central maximum. But n has got to be consistent with it. What would n be in this case? 1 minus 0 is 1. What would n be in this case? What is it? 3.5. Does that make sense? Okay, we'll finish this stuff up tomorrow, guys. Do an example problem and some practice problems. The only homework you have is to finish up that check and reflect page tonight. Let's get those done for tomorrow, and then we'll continue on with this tomorrow, okay? Have a good night, everyone.